Lei, welcome to Validate It.
Very nice to be here, and thanks for inviting me, Austin.
Yeah, I'm excited to talk with you today and talk about the MegaETH project. I first learned of you guys back in, I want to say like 22 or 23, so it was like pretty early on in the process. And what caught my mind initially was you guys were the only folks who were looking at specialization of nodes.
Mm-hmm.
And I think this is one of those things where like we've looked around the industry and seen a lot of stuff that feels very similar. Like most L2s are fairly similar. Sometimes you have some ZK coprocessors thrown in there for some fun, but they're primarily treating the act of sequencing and the act of cranking execution on a sequencer very similar to the way you treat it on an L1 network, right? Which is you have a validator that does block building, it does block execution, it reaches consensus, it propagates the block out. But you guys started with a little bit of a different vision. So I want to get into all the fun stuff about like what makes your entire conceptual model different. But I kind of want to start out with like maybe the obvious question, which is why do we need a new L2?
Well, it's a very interesting question. We got asked about this many times. So my answer would be that existing L2s are not just bald or performant enough. And we think that we kind of want to enable brand new applications. And we don't think that just boosting the performance, say boosting the throughput or reducing the latency by 10 times is sufficient to give you new applications. You might be able to run, say, Uniswap 10x faster, but that's not exciting to us. Instead, we want to really kind of design a platform or show to the builders, hey, it's now possible to design a whole new class of applications, like real-time applications, real-time experiences, because the infrastructure is now ready. And we don't really see any other L2 when we were launching that are actually targeting this, I would say. So yeah, that's why we decided to do it.
Yeah, so I hear this a lot, right? MegaETH is like targeting real-time blockchain applications. If I'm a user of Solana or I'm a user of Base, like it feels pretty real-time. I click the button, the swap happens. Like, what does real-time mean to you that is, in your view, missing from the rest of these networks that are like pretty fast and can do execution pretty quickly? Like, what is the jump there between like the 400 to 800 milliseconds on Solana or like Aptos or Sui, and then what MegaETH is targeting with its definition of real time?
Yeah, the core difference here is really the kind of the frame rate or the block time, if I may. So yeah, you mentioned the number 400, 800 millisecond. I think there are L2s that can do as low as 250 millisecond per block. But if you compare that with, say, the frame rate when you see when you're playing a game, right? 60 frames per second is kind of the standard for gamers, and that's about 16 millisecond per frame. So this is a very small number compared to the 250, 400 millisecond like refresh rate for your normal blockchains, and also if you look at the like how fast high frequency trading happens in TradFi, it's much lower. It's much lower interval than the several hundred milliseconds of time. And another aspect, which is also I think equally important, is that the chain has to be able to sustain this level of performance when it scales to a large number of users. And with say several hundred transactions per second, we don't just see that happening.
Yeah, so we're gonna get real deep real quick just to prep the audience. So there's an interesting thing that happens in the TradFi space, which is if you look at like NYSE or you look at NASDAQ or you look at CME or you look at Nikkei, they're all effectively cranking execution very quickly. Orders come in, orders are filled, orders are confirmed, right? That period of time is extremely, extremely fast. The downside of that is it's impossible to profitably trade on one of these exchanges without being co-located, right? And so a lot of times you see like there's networks that have like, one of my pet peeves of this industry is like we just take words that mean things and pretend they mean different things. Like blockchain latency is like a totally useless term nowadays because what people mean is once it's already in the system, how long does it take to process? But anyone who's worked in TradFi knows that 99.99% of the time is actually the speed of light as your limiting factor. It's the time it takes to get a photon from Singapore to New York. right? And so if you are looking at building systems that can do 16 milliseconds, right? The RTT to Singapore is at least 250 milliseconds, even on the fastest connections nowadays from New York.
Yep.
You end up with a asymmetric information environment very quickly. And so part of the question is like, how do you think about reaching consensus and moving the state of a sequencer faster than that data, like not even faster from a technology standpoint, faster than the speed of light allows you to propagate it out, while also thinking about building global systems? Because you're spot on, right? Like blockchain systems today are astronomically slow compared to TradFi systems. But the inverse there is that TradFi systems are inherently regional because of the speed of light constraints. So when you're thinking about building like an L2, are you like inherently, is there an assumption here that L2s that are fast are also going to be regional, and we just sort of need to I don't want to say get rid of the idea of the world computer, but like rethink that model, because the speed of light just won't allow it to be an equal access state?
I think you're definitely right that at any given point of time, if there is one machine and there has to be one machine that is actually running the transactions, then the distance to this machine is different depending on where you're sending the transactions from. And yes, the kind of the feedback loop, the network round trip time, the RTT will be different. Yes, from New York to Singapore is at least 200 millisecond round trip. But on the other hand, if you see the volume of today's trading, I don't think there's any issue with, say, a really professional high frequency trader just having co-located servers in all of the major stock exchanges in the world.
Yeah.
So I think my viewpoint would be that yes, depending on how close you can co-locate, kind of shrinking the block interval, shrinking the kind of the actuation time in the system will kind of start to expose this this difference in your network connection, right? So because let's make an example, right? So with Ethereum, for example, 12 seconds per block. Me having a, let's say, 500 millisecond round trip time to my node to someone else having a 1 millisecond round trip time is it creates a kind of a negligible difference because it's like 500 milliseconds over 12 seconds.
Right. Only 2% of the Ethereum block time is execution. 98% of the Ethereum block time is just for networking stuff.
Yeah, exactly. And shrinking this block time will start to expose this difference. So I would say this is a very interesting exercise for traders, but I don't necessarily think it's a bad thing, because ultimately it improves market efficiency that you can trade at that level of frequency. Because if we don't do it, if no layer 2 does it, Binance is going to do it. Binance probably already doing it. They are probably like matching trades less than 12 milliseconds per trade, right?
I hope so.
Yeah, I do. So I would say that competition is not within the blockchain ecosystem or the kind of the decentralized blockchain ecosystem. It's against TradFi. And to compete against TradFi, you cannot just say that, hey, TradFi, please slow down. We have to speed up. And we have to get all of our infrastructure ready to be able to compete with them. Say, co-located servers, really fast, really stable networking, etc. Yeah, so that would be my point.
Yeah, it's funny, and not to turn this into an ad for 00, but like one of my co-founders was telling this story about I think what it was 2018. There's a whole bunch of this story I have to gloss over details on because I'm sure a bunch of it's under NDAs, but where they were building this new execution network using like wireless links the same way you would in TradFi. And they were basically saying, oh, we're gonna make so much money because we're gonna have a faster connection into this like crypto exchange. And they spent a ton of money. They built this thing. They thought they were gonna be way more profitable. And it turns out that the exchange execution was just so goddamn slow that it didn't matter that they had faster network links, because just like you're talking about, if you got a 12-second block time, it doesn't really matter if you're faster because there's no incentive to be faster.
Yep.
But like, I think one of the pieces that so if we take the TradFi example here, people like there's this idea that, oh man, it's all in the execution. It's all in like how good are your quants and how good is the exchange at processing trades. And the reality of it is the quantitative models are very important, but the thing that actually makes you money is execution speed. And execution speed is downstream of networking. And so it's really interesting to kind of look at these. And so I want to get into like how you guys have thought about data flow and data movement and how this gets into node specialization. Because I think it's very easy to sort of say, we're going to build a server, we're going to throw 8 gig of gas at it, we're going to throw, 5 thread rippers at it, and like it's going to be incredible.
Yep.
And sure, right? Like there's parts of that very much maybe, but like there's a whole apparatus around doing the thing that actually changes the thing from like an academic lab project into like a production environment that can compete with TradFi. So like walk me through a little bit of like from a data flow model, transactions come into the MegaETH system. What happens next?
Yeah, it's very interesting, a very broad question. Transaction comes into the MegaETH system, and now we have to define what coming into the system means, right? So we envision that there should be a ring of like an outer ring of servers that each has an up-to-date state snapshot of the system, so that they can very effectively filter out spams, basically transactions that has no chance of like succeeding. And then these transactions will be forwarded from this outer ring to the core sequencer, and it's at any given point of time, there's one sequencer, but we do plan to rotate the sequencer, because I think you made a very interesting point previously that yes, basically this asymmetric information advantage exists, and we do want to kind of distribute it as evenly as possible. So we think that actually rotating the sequencer by the hour, or say following the sun would work. So but back to the topic, at any given point of time, there's one sequencer, so the transactions are aggregated there. The sequencer executes the transactions, of course, 5 thread reapers or more, I don't know. So now it outputs 2 kinds of data. One is we would call it a state delta. So it's basically the difference, and only the difference, before and after a transaction or a block of transactions is executed. So with this delta, you can stream these deltas. I'll talk about how we stream the data, but you can stream the deltas to what we call replica nodes, who are just listening for those deltas and applying them, patching them on top of their local databases, so they can serve as read replicas to whomever that is interested in the latest blockchain state. So this is kind of the state deltas. They don't need re-execution. And on the other hand, you have transactions themselves, and accompanying the transactions, we can optionally insert something that we call witnesses, that allows a node, which we call full nodes, to re-execute the transactions without maintaining a local replica of the state. Of course, they can choose to maintain local replica of the state, but with the witnesses, they don't have to. So this would enable pretty lightweight full nodes that locally verify transactions, but probably their hardware consumption is going to be just 100 or 1/10 of the sequencers. So now we have covered transaction coming into the sequencer, being executed with the states deltas, and the raw transactions streamed out to replica and full nodes respectively. And finally, we have a global mesh of prover nodes. So at the very beginning, we're planning to use optimistic proofs, but we'll later evolve to ZK proofs when the cost of ZK proving per transaction goes down. And the stuff that streams to them are also the witnesses and the transactions, so that they can locally re-execute them to generate the proofs. And also, like one layer below, we have, of course, Ethereum, the layer 1 serving as the security anchor, and EigenDA serving as the data availability layer, which just kicks in when the sequencer just refuses to provide the data to anyone in particular.
Right. So I want to walk through kind of a few pieces. So the sequencer is doing inclusion and execution, or is it only doing inclusion?
It's doing both inclusion and execution.
Okay. And so I want to kind of walk through like a few pieces in this, because one of the things you mentioned is outer ring, right? And so outer ring designs, they've been used, like Qtum used them back in like 2017. It was the Libra structure. I think there's a few other networks that look at using them. Solana has some version of this that's not exactly that, but it uses stake-weighted QoS as sort of a way to proxy stuff to reduce spam. The downside of most outer ring designs is that they introduce an additional network hop, and getting in and out of an x86 machine is not the fastest operation. So I'm kind of wondering, like, there's a few pieces that you sort of have talked about here that all are around execution. And this is why like the data flow question is always so interesting to me, is like, what is the sort of like the latency you introduce on the outer ring? Because if you can, for example, have 16 millisecond block times or 10 millisecond block times or 1 millisecond block times, but the effective latency to get into a system like once you hit the outer node is like 10 milliseconds, you're just running a slightly different type of system. So I'm kind of curious, like, how does that structure, like from a data flow perspective, work? And then what is the sort of the latency model look like in terms of, like, as you mentioned, once you're witnessing data and once you're sort of doing state replication, those are not free operations. Like, what does sort of the state lag look like?
Yeah, so I think there are two types of like transaction sources: those that are outside of the outer ring and those are inside. So the latter kind would be for like professional high-frequency traders who are willing to collocate with our sequencer and even rotate out with our sequencer, or just kind of get situated in within this like core network, right?
Yep.
And for them, this filtering won't work, right? They are probably staking something. They're probably like signing a deal with someone, committing to like not spamming the system.
Right.
It's kind of a semi-permissioned.
Very similar to how TradFi works, where you pay a fee, and if your server starts misbehaving, they pull your network plug.
Yep, exactly. It's I mean, in a blockchain case, it might not be a fee, but say a stake or something, right? But similar. So yeah, I think your question was mainly on like for the nodes who are situated outside of the outer ring. I would say yes, it does incur extra latency to relay those transactions through the NIC of an x86 machine, the CPU running spam filtering, and then the NIC again, right? So, but I would say this latency so host networking stack is usually pretty lightweight compared to the speed of light propagation delay. So I would say that the extra time would be 1 to 2 milliseconds to do all of those filtering and of course the packet ingestion and transmission, right? So let's kind of just put those numbers in respect to each other, right? So, like actual operation of spam filtering, 1 to 2 milliseconds. The original distance from a user to, say, the edge of the outer ring, I would say 10 to 200 millisecond round trip, or 5 to 100 millisecond one way. And then and then say from the outer ring to the central sequencer, I would say maybe 10 to 20 milliseconds, because the outer ring can also rotate with the sequencer.
Okay.
So yeah, kind of looking at those numbers with respect to each other, one would see that this extra hop of filtering does not really add too much latency compared to the kind of the original like speed of light propagation time that a user has to pay anyway.
Sure. So what do you define as spam in this case? Is it just like signatures that fail verification? Because spam is defined by different people in different ways.
Yeah.
Like what is appropriate censorship at the filtration layer, and what is inappropriate censorship at the filtration layer?
Yeah. I would say for a blockchain, as long as gas fee can be collected, it should not be considered as spam. So I think you're mentioning censorship. It's very interesting. I think it's the correct way to classify spam filtering, right? You basically want transactions that has no. I think I actually used that definition at the very beginning. So you want to filter out transactions that has no chance of getting onto the chain under the current state, under say the content of the transaction, right? But all the other transactions, you should give them a chance to arrive at the sequencer. Because if not, then you're kind of biasing towards one. It's inevitable that you're biasing towards one type of transaction over another. So yes, as you mentioned, just incorrect signatures, insufficient gas, or like insufficient gas price, etc. So these kind are the ones that we want to filter out.
No, it's a good clarification because when you said transactions that have no hope of executing, there's plenty of transactions included in a Solana block that have no hope of executing. Like, for example, I might be trying to liquidate you and your loan is not in liquidation yet, but I'm willing to pay the fees on the off chance that between when I send the transaction and when the state updates, it falls into liquidation. That would be allowed under the MegaETH filtration model.
Correct.
Even though that transaction, we know it would, like if I submit an order that's paid for, but I want to buy Ether for $10, obviously that transaction is going to fail, but it's valid from a payment perspective.
Yep, exactly. In the case of Ethereum, I wouldn't really call it like a transaction that has no hope of getting executed. It will revert, the gas fee will be collected, and the transaction will actually appear on the chain. Yeah, it's failed. Like if you look at Etherscan, but we know what we mean. So
this is the oldest FUD debate in Solana, where the transaction succeeded. It just succeeded with no state change.
Yeah, it's not. Yeah, it's not. It's
like
not
a reverted
really spam,
transaction
right?
did execute. It just didn't result in a state change.
Yeah, it's opportunity cost, right? The gas fee is the opportunity cost that the person is willing to pay. So we should give them the chance.
Yeah, interesting. So then once the sequencer has produced a block or whatever logical unit you're using, there's kind of no blocks on L2s, right? This is like the whole thing. But once a sequence, would you disagree with that?
Yes. Conceptually, you can stream out transactions like one by one. You execute transactions on like byte size, right? One transaction at a time. But engineering wise, it's very hard. It's really, really hard to commit to, especially in Ethereum land. It's very hard to commit to state roots at really high frequency.
Yes. But then once that data has been processed by the sequencer and is ready to be propagated out, how does that then work? What is the data flow model there look like?
Yeah, so it's almost similar to a tree, but actually multiple trees. So we are kind of envisioning the data flow network coming out of the sequencer like in two levels. One is a core network, or like a peacetime network that is really high performance and maybe more trusted in terms of trusting individual nodes in the network. And another like a backup, always online network that is not really trusted. So we have been focusing on building the latter because we think that actually to build the first like this high performance network properly, it's inevitable that you have to like re-architect the internet. You have to get your own fibers. You have to get your own POPs, right?
Imagine that.
Yeah, so we have been focusing on the second kind. So basically, bootstrapping an efficient peer-to-peer broadcasting network, streaming network on top of the internet. So yeah, I spent actually a few years studying this topic during my PhD at MIT. So it's kind of the perfect problem for me. So yeah, we actually noticed that Ethereum already has a pretty robust network protocol called DevP2P, but the issue is that it incurs too much redundancy. So basically, for each like piece of data that a node receives, it's going to actually receive 4 to 8 copies of the same piece of data. So a redundancy factor of 4 to 8x. So that means that if your computer has, and on the other hand, we do hope that users can install a node at their home with probably a 300 megabit per second Comcast downlink, right? So, but a redundancy factor of 4 to 8 times means that, with a 300 megabit per second link, you can only get to maybe about 50 megabit per second of useful data into your home. So it's not really working for us. So we kind of decided to just use a broadcast tree. It's a bit similar to Turbine in Solana, but it's not coded. We don't think UDP, it's just a design choice, but we don't really want to use UDP. So erasure coding is not that important. And also Reed-Solomon encoding I would say at Solana speed would be fine, but at MegaETH speed, I think it's actually going to be a CPU hog. So we just decided to do no coding, pure TCP broadcast tree, but multiple broadcast trees to make sure we can use people's uplink bandwidth as well fully.
How do you handle the retransmit problem without erasure coding?
Yeah, good point. Retransmission is handled by TCP. So so basically there are kind of two common networking protocols on top of the IP layer. So UDP, which is like no guarantee of reliability, no guarantee of in-order delivery,
Spray and
and
pray.
TCP is the reverse. Yeah. And TCP is the reverse. It guarantees reliability and in-order delivery. Yeah.
Yeah, but TCP is also very slow because of that, especially on like the reason people obviously, I mean, you TradFi background, right? The reason people use erasure coding and Reed-Solomon encoding is so you can recover data without having to send a request out to the server to then wait for it to be fulfilled and then have it kind of come back to you. So these are the interesting questions for me, because as we build faster and faster blockchains, the data transmission becomes like the usefulness bottleneck at some point. Like if you can't get the state updates to know how the market is moved, you can't submit a new transaction to execute based on where the state is. This is already a problem on a lot of networks. Just state propagation is like over the public internet. It's kind of hard. So I'm kind of curious. Like if let's say just like Comcast drops some packets, not a crazy thing to imagine Comcast doing, or how do I then as someone who's running either in a home server or on a data center server, like what am I talking to get the state that I'm missing now?
Okay, so first realize that the TCP happens over like your neighbors in the P2P network or neighbors, immediate neighbors in the broadcast tree. So always you ask for the packet, for the lost packet from your upstream, and also this is done. It's kind of transparent to the upper level protocol. So we are designing an upper level protocol that builds on top of TCP. And TCP provides us with an abstraction of a reliable pipe. No packet loss, no out of order delivery, because it abstracts away these errors. So when there is a packet lost, the receiving end's in-kernel TCP stack will realize that, hey, there is a missing sequence number. So every TCP packet has a sequence number that increases by 1 for every new packet. And if there's a missing sequence number, then it realizes, hey, there's probably a packet lost. And it will probably wait for just a few more packets, because there probably have been a kind of out of order delivery, and maybe the packet would come. But if not, then it's going to ask for a retransmission. And basically sends an ACK, a negative ACK to the sender, to the upstream, and the sender is going to retransmit the packet that is lost. So you are definitely correct that it takes one extra round trip time to get this packet delivered. But it's by injecting redundancy into the packets themselves, yes, you can you can kind of recover from the error without really asking for a new packet, which I think is what Turbine's doing, but I think it's kind of a trade-off, right? You're basically injecting redundancy during peacetime as well, to prepare for the inevitable packet loss. So it's kind of a trade-off between error correcting latency and just normal time bandwidth overhead. By the way, there are also papers trying to do this in TCP. It's called coded TCP, serious papers, very interesting ones. Yeah.
Yes. So what is the data rate that you guys are targeting for then? Like Solana really does not work on a 500 megabit upstream downstream connection. Mainnet says they're targeting 100. Most L2 sequencers require multiple gigabits nowadays of it. Like if you're trying to walk the state to be able to run like an RPC server to submit transactions, like as you mentioned, kind of like a home verifier, what's the rough data rate you need to be able to handle?
Our calculation was 300 to 500 with MegaETH like near term throughput goal of like tens of thousands of TPS, with non-trivial state changes. But network, I would say, is by far the most immediate bottleneck once we start to
Yes.
scale beyond that goal. And yes, so a million transactions per second is not a big trouble for the sequencer if you throw enough hardware at it. And at that point, network would have to be multi-gigabit per second, of course.
Yeah, so this is kind of like I've asked Keone this question too a few times, which is sort of like the minute you get past the Bitcoin thing, right? Like I think the Bitcoiners are like the ultimate left curve here, and they're spot on, which is like I want to be able to verify a block from an FM radio transmission from a satellite in orbit. And like I can do offline verification of the Bitcoin ledger. That's super cool, right? That is kind of like if you think about sort of like the full left curve idea of it, it's like, okay, totally offline verification. I have complete self-sovereignty over my assets. Like we know what Bitcoin's good for. Great. Then you go kind of full right curve and you're just like, look, man, like just put it all in a data center. Like we put 20 gigabits into every node because realistically, not many people can get access to a 500 megabit connection in their home internet connection, right? Fiber is getting more common in residential services, but it's still not super, super common, especially in most of the world. And so if you're going to set a floor of 500, why not just set a floor of 5 gigabits? Because the access difference in like raw number of people between like if you're in Asia, if you can get a 500 megabit connection, you can probably get a 5 gigabit connection. Not in the United States. The US is a bit later on that. But like walk me through kind of like the thinking of where that 300 to 500 comes from and sort of why from the start you guys aren't just being like, look, like let's be real, like we're just going to go for maximum performance and say we need 5 gigabits.
Yeah, good question.
Or 50 gigabits.
Yeah, good question. And I definitely get the taste of the Bitcoiners. I operate amateur radio. So tell me about
you get it.
1.6 kilobit per second radio backhaul, right?
Yeah.
Interesting. So the 300 to 500 megabit per second number was calculated from the TPS goal. It's not like the limit. So we kind of the logic. The flow of logic was that we first wanted to do a blockchain of tens of thousands of TPS, and then we kind of back calculated how much bandwidth it's going to cost. And 300 to 500 is a very, very conservative in the sense of being an upper bound of bandwidth that we need. So I think it's like we are starting out, and we do want to deliver something to the world as soon as possible. So we think that several tens of transactions per second, tens of thousands transactions per second is a pretty good goal compared to what the EVM land is offering. And the network bandwidth number is not that crazy. I would actually argue that there is a significant step function change from hundreds of megabit per second to over 1 gigabit per second. Just judging from my personal experience of signing contracts with residential Comcast service. And also, once you go over 1 gig, I think many of the homes need to get their network cables replaced, switches replaced, routers replaced. So I would say there is some kind of significant difference. Why do we still plan to go over that? Because I think actually we don't think many users care about having access to the entire state in real time. Maybe I'm a retail. I just want to kind of get my own wallets updates. Maybe I'm a dApp developer and I want to host my own RPC, but I only care about the states under my own contract, right? So if we go faster than that, we can still provide useful service to people who don't want to subscribe to a multi-gigabit per second network link. It's just basically more specialization, which is inevitable. Yeah.
Sure. So I kind of want to change a little bit and now talk about like smart contracts. And the reason for this is there's sort of this like weird debate going on Twitter at the moment around like, do we actually need faster networks? Do we actually are there actually only 6 smart contracts that matter? Right. And this is sort of like a thing that we've seen come up in the last few days. And I think it's largely come from L2s that have no hope of actually reaching multiple thousands of transactions per second. I'm not exactly sure like where it's come from. But, you are working on a network that aspires to tens of thousands to eventually hundreds of thousands of transactions per second. What's your thesis on why the EVM needs that? Why is the several hundred, the low single digit hundreds that have been doable for the last year, 2 years, not sufficient? And why do we need a tenfold, hundredfold increase in transaction capacity?
Yep. So I think I touched on this point at the very beginning. Why do we need another layer 2? And why do we need to scale the throughput so dramatically? I think it's really because we really, really want to bring new applications to crypto. And again, if you scale the throughput by 10x, maybe each transaction costs maybe 5% less, 10% less. Maybe you don't have gas wars as often, but I don't think it enables new applications because when we talk about TPS, we also have to worry about the computational complexity. 300 TPS ERC20 transfers is very different from 300 TPS club trades, right?
It is.
So as you scale the throughput, when you denominate in TPS, a byproduct is that you're also scaling the computational capacity. So that fundamentally allows you to build more complicated applications on chain. So I think there have been multiple attempts at building clubs on EVM and EVM chains, but I don't think any fully on-chain club has really took off at this by this point. I would attribute that to just the low computational capacity of EVM chains. So this is one example.
Yeah. So I want to kind of dive into a little bit of how you guys are solving for that, because one of the criticisms and advantages of Solana is that programs have to specify all of the accounts, all of the state they want to talk to before they execute. This is like a very intentional decision that comes from like old school microarchitecture, which basically says like, hey, if I know everything you say you're going to touch, it's very easy for me to parallelize these transactions because I can look at this pool of data and say, okay, all of these are not overlapping. I can execute them simultaneously. EVM doesn't work that way, right? EVM was originally designed to be one transaction at a time, and so there was no need to put limits on where a transaction could spiral out, and it gives you cool things like the ability to take out a flash loan and do a trade and pay back that flash loan, but it also means that like it is extremely difficult to guess what a series of EVM instructions are going to do on a more complicated transaction like you're talking about before you actually crank execution on it. So like Mainnet has done a lot of deep pipelining, and there's a certain amount of just like stochastic reversion that is going to inevitably happen in their execution because they're going to get it wrong sometimes, right? This is the same thing. I mean, like, this is out of order operations. x86 processors do this all the time. This is not like groundbreaking computer science stuff or like a dig at, Mainnet or something like that. But it is a problem that you have to think of when you're not using limited instruction sets. So like, how have you guys thought about that problem? What do you think the sort of like reversion overhead is on MegaETH? And how do you prevent the sequencer from basically sequencing stuff that ends up overlapping?
Yeah, so I would say it's kind of a design choice. Yes, Solana decides to. So this overarching problem is called concurrency control, right? So yes, and it's fundamentally true that in order to schedule transactions to be run in parallel, you have to somehow figure out if they are kind of causing conflicts. And I think Solana's decision was to kind of push this problem or offload some part of this problem to users' wallets. So now it's the users' wallets or the dev developers' responsibility to figure out what states Solana transaction has to touch, right? On the other hand, I think all EVM chains, if they are trying to preserve compatibility with EVM, they have to do this on the fly when the transaction already hits the sequencer.
Yeah, one of the main differences, just to sort of expand on that, one of the main differences in Solana is the dApps build transactions, whereas for most EVM systems, the wallets are the ones building transactions.
Yep. So but I think the thing is that without access to the latest state at which point that a transaction is being executed, it's impossible to tell in advance the set of states a transaction is touching. So, and this is true even for Solana, right? We have those reversions on Solana because ADAP is not able to correctly estimate the set of the set of states that a transaction is touching. And then when it arrives at the sequencer, the validator or the block builder, they realize that, hey, this transaction is trying to access and kind of an unauthorized state slot, and this is basically now inexecutable, right?
Yes.
So it's a trade-off. I think Solana's trading off is kind of preferring simplicity in validator's implementation, especially the parallel scheduler, over, I would say, UX or complexity in the apps. The apps has to do much more things, like doing static analysis, doing dynamic analysis to figure out the states. So I would say it's a trade-off, and it's not. Yes, I would say it's just a trade-off. And for MegaETH, what the reversion overhead will be, because exactly we don't require the transactions to pre-commit to the set of states that they're going to touch. There's not going to be reversion as that are of the same nature as reversions in Solana because of incorrect estimation of the states going to be touched. Yes, it's harder to build a scheduler. It's harder to build an efficient scheduler without that kind of information.
Yeah.
But yeah, so I think
so. Walk me through a little bit of like. Yeah, I want to get into kind of like because every parallel EVM or attempting to be parallel EVM, we can debate how much some of them actually are parallel, has to solve this problem. And I'm really curious how you guys have thought, because you're targeting a much higher transaction throughput than most parallel systems are. Like I'm curious how you've thought through and what are the design decisions you've made around how that actually gets done at a fast enough rate to support tens of thousands of transactions per second.
Yep, very good point. So the key thing here is that you want to use the correct scheduler algorithm. So not all algorithms are created equal. So some of them will give you more wasted work. Wasted work in the sense of like attempting to execute a transaction and then having to reverse and kind of doing the same transaction again in sequence to another. So the key thing here is to kind of design the scheduler in a way that minimizes the wasted work. And the second important factor is that there should not be starvation of transactions.
Yeah.
So there's something called a cascading abort in a class of concurrency control systems that basically says that you kind of took the risk of executing a bunch of transactions in parallel, only realizing that you have to abort all of them after you have done almost all the work, and then you redo it, and you take another you take another risk, and the same happens again, and at the end of the day, it takes you so many iterations to figure out that, hey, these transactions have to be executed in strict sequential ordering. But by that time, you have already wasted so much work. So this is
right, and the depth of your pipeline. The depth of your pipeline determines how much reversion. This is literally what killed the Pentium 4 architecture.
Exactly. So yeah, exactly. Yeah, I mean, branch predictors is we all love branch predictors. We all love caches, but yeah, I would also love my computer to just be as simple as my textbook says. So yeah, I would say this is the key to try to minimize wasted work. Now that you can only guess, you don't have that information that Solana people have. You have to take the guess, and taking the right guess and not risking too much, kind of balancing the risk that you take that might give you increased parallelism, but at a kind of greater risk of cascading aborts. Kind of balancing the two factors is the most important thing. I cannot dive into more details, but I'll just claim that this is the hardest problem.
So how much is like an acceptable reversion or failure? Because like I think there's a lot of different ways to think about this, right? One is like erasure coding, as we've talked about, is an overhead that Solana has decided, this is a fine overhead. We're willing to accept this. Inherently every EVM parallel system has some amount of getting it wrong overhead that they choose to accept? Like, do you have a sense of sort of what is an acceptable, like if you guys launch and you see like, there's an overhead rate of 5% or 15% or 25%, like what is sort of the acceptable rate? And what do you think is kind of like in a mature, well optimized system, like what the sort of theoretical rate gets closer to being?
The theoretical rate is always 0, and
Sure,
that's. I think you use the word mature, and I think that's a very important qualifier because it's not just the job of the chain. It's not just the job of the sequencer. It's also the job of the app developers.
Yeah.
If say you're designing a club that is going to see a lot of access, it's actually the job of the app developers to shape the smart contract in a way that minimizes conflicts.
Yeah.
And I think this is a much more interesting thing to work on because all those concurrency control algorithms are I would say they are well studied by the end of the 80s by the database people.
Yes.
I literally wanted to work on a project and my advisor just advised against that, saying that hey, it's all like reincarnation, like incarnations of the same stuff, right? So I think for the blockchain community, for crypto, I think getting a generation of dApp developers that are comfortable with writing like parallel code is much more important than kind of shoehorning on the scheduler algorithm. I think that applies to Solana, that applies to Ethereum, despite the difference of how the two ecosystems treats parallelization scheduling, right?
Yeah.
Because I think with Core 2 processor, I think with multi-core CPUs, we got a bunch of developers that are comfortable with writing message passing programs, right? I think we need the same thing to happen for the blockchain community. Really, yes, I think it's very interesting and very important.
Yeah, we went through this crazy transition from like single and dual core processors to multi-core processors. But at the same time, we'd ruined an entire generation by teaching them the program on cloud systems and teaching them that compute is magic, memory is magic, network is magic. You can just always throw more hypervisor resources at it, meanwhile accepting a 25% performance hit for running in the cloud.
So true.
I think that's the end of that rant.
This is so true.
Well, the last piece I have to ask before I let you go is around timelines. What does it look like for you guys to be kind of rolling out into like wider testnet, mainnet? What's the kind of next steps people should look forward to on MegaETH?
Yeah, of course. So we launched the public testnet a few weeks ago. We're now onboarding the apps and infra partners. A wider, like a more, like I would say it's already publicly launched, but a wider like community facing push would happen in a few weeks. Basically, we need a bit more time to onboard the apps and the infra. And a mainnet, I would not allude to any precise timeline, but working very hard on it.
So let me maybe I totally get the timeline question. It's very hard to answer. What would indicate to you that you're ready for mainnet?
So we want all of our initially planned optimizations to be live and to be well tested, to be well documented, to be well benchmarked. We want a solid security model where an Ethereum Layer 2, and we want to be very proud of the security guarantees that comes with it. And we actually want to see a vibrant community of infrastructure partners. I think we touched on this point during the podcast. Basically, we think getting a sequencer fast, getting a bunch of full nodes that can synchronize with the sequencer is, I would say, just half of the work. The other half is getting the explorers, getting the RPCs, getting the indexers ready. We're working on something interesting on each of the front, and we also want to see that kind of work to mature by a bit before we launch the mainnet.
Awesome. Well, Lei, thank you for joining us today on Validated.
Thanks so much. I really enjoyed the chat.